Good morning. Today we're going to talk about Chapter 6, Exponents and Polynomials, and in particular Section 6.1, which is entitled Exponents. Alright, so today we're going to review properties of exponents, and in particular rules and stacking of rules for exponent expressions. Well, as a brief review, if I've got 2 raised to the third power, 2 we refer to as the base of this exponent expression, and 3 is, of course, the exponent value. 2 to the third power, it's really a shorthand for multiplying together 3 factors of 2, 3 factors of your base, and of course 2 cubed is equal to 8. All right, let's talk about some variable values. Let's see, I've got a variable expression, x to the fourth power. Well, all that means is you take your variable base here, x, and multiply it by itself 4 times. So x to the fourth power really means 4 factors of x, where a factor is an element of a product. Okay? All right, let's investigate the first of our many rules for exponents we're going to talk about today. Let's say I've got x squared times x to the third power. All right, well, that just means I've got 2 factors of x, that's x squared, times 3 factors of x cubed, and of course x squared times x cubed, I'm going to have 5 factors of x all being multiplied here, and of course by the associative law I can multiply these factors in any order I like, so really I can say this is equivalent to x to the 5th power. Let me make that a little clearer. X to the 5th power. All right, which suggests a rule in general. And indeed, if I've got x to the mth power, an unspecified exponent, times x to the nth power, indeed, I'll just keep that same base and add the exponents. So x to the m times x to the nth is x to the m plus nth. Okay? All right. As another simple example of that, let's say I've got y to the 4th power times y cubed. Of course, it's going to be y to the 4 plus 3 power, or y to the 7th. All right. Our book calls this the product rule for exponents. And this is on the bottom of page 344. All right, so we'll be highlighting these rules for exponents as we go along in the video lecture today. All right, if we look at example 4 in our text on page 345, let me write that down, example 4 on page 345. Well, we suggest there might be a similar rule when dividing exponent expressions. Well, the book says in example 4 to divide x to the 5th by x cubed. Well, if we do that, that's equivalent to writing it in a fractional sense, x to the 5th over x cubed. Well, of course, if I've got 5 factors of x in my numerator, and I've got 3 factors of x in my denominator, of course these factors in the denominator will cancel out corresponding values of the variable in the numerator, and leaving me essentially with 2 factors of x in the numerator and a 1 in the denominator. And of course a divisor of 1 is redundant, so I would just call this x squared. And of course you can get from here to the final answer just by subtracting the numerator, the denominator exponent from the numerator exponent. All right, the rule that this suggests in general, again, this is in the middle of page 345. The book calls it the quotient rule. for exponents. Another one of our rules for exponents today. And it says this: x to the nth power divided by x to the nth power. It's an n there. Divided by x to the nth power equals x to the m minus nth power. All right, so when we multiply the same base expressions, we keep that same base and add the exponents. Somewhat similarly, when we divide exponent expressions, we keep that same base and subtract the exponents. In particular, subtract the denominator exponent from the numerator exponent, right? All right, some simple examples here. Let's look at example 5 in our textbook. If we want to simplify the following, if I've got 3 to the 5th power over 3 squared, no, I'm not going to go run to the calculator and do things more complicated than we have to. I'll just write this as 3 to the 5 minus 2 power. Well, 5 minus 2 at the exponent level is 3, and 3 to the 3rd power, of course, is 3 times 3 times 3 is 27. All right, also simplify. This is, all right, the first example I did here was example 5, part A. Let's look at example 5, part B. 6 to the 4th power over 6. Well, 6 to the 4th power in the numerator is divided by 6. 6 is really 6 to the 1st power. We've got one factor of 6 in the denominator. And of course, I can write this as 6 to the 4 minus 1, which is 6 cubed, which is 216. Simplifying finally. Let's look at part C. Again, invoking the same rule. X to the 12th over x to the 5th. Now, of course, we're not going to write out 12 x's in the numerator and 5 x's in the denominator. We'd be here all day. Let's invoke that rule, a quotient rule for exponents. X to the 12 minus 5 is, of course, x to the 7th power. Simplified. D, in example 5, y to the 10th over y to the 8th is y to the 10 minus 8th power is y squared. And we're hoping eventually, if you do a few dozen of these, you can skip right to the final answer in many of these types of problems. Part E in example 5, z to the 8th power over z. Well, of course, in the denominator, z is just z to the 1st power, one factor of z in the denominator, and hence invoking that rule, z to the 8 minus 1 is z to the 7th power. You may notice in the previous example 5, all the exponent expressions in the numerator had exponents that were greater than the exponent in the denominator. And you may ask, well, what do we do in the other case where you've got denominator exponents that are greater than the numerator exponents? For example, x to the 9th over x to the 12th. Well, I suppose we could write out 9 x's here and in the numerator and 12 x's in the denominator. Let me do this a little more quickly. I can say that 9 factors of x in the denominator, 9 factors of x in the numerator will cancel out all but 3 factors of x in the denominator, right? So I'm left with 1 over x cubed. All right, final answer here. Oh, and let's say part B, this was part A in example 6, part B, y to the 4th over y to the 9th. Again, 4 factors of y in the numerator will cancel out 4 factors of y in the denominator, leaving 5 factors of y in the denominator. Okay? Final answer here. All right, let me get a fresh screen. Scroll up. All right. The author next talks about example 7 on page 346. And again, they're trying to motivate here yet another rule for exponents. So far, we've had the product rule for exponents. We've had the quotient rule for exponents. Now we're going to talk about the zero exponent rule. All right. The author says here, divide the following expression and simplify. Well, if I've got x cubed over x cubed, well, I suppose if I invoke the quotient rule for exponents, we've got x to the 3 minus 3 power. But of course, 3 minus 3 is 0 at the exponent level. And certainly we know when we divide identical expressions like this, we know it's equal to 1. All right, so this gives us a motivation to discuss a new rule for exponents called the zero exponent rule. And it states that x to the 0 power is equal to 1. Let me write that down. Zero exponent rule. It says x to the 0 power equals 1. No matter how simple or complicated the base is, raise it to the 0 power and you get 1. This is example 8. On page 347, let's look at part A. 3 to the 0. Simplify each expression. And of course, 3 to the 0 power is going to be 1. Anything to the 0 power is 1. Right? Whether it be a numerical base, as in part A, or a variable base in part B. Right? X to the 0 power, always 1. Let's look at C. Now, don't get confused here. 3 times x to the 0 power. Well, that exponent does not see the 3 in this operation. There's an order of operations that says do the exponent expression first and then worry about the implied multiplication here. So let me rewrite that. 3 x to the 0 power is really equivalent to 3 times x to the 0 power. X to the 0 power is going to be 1, so 3 times 1 is, of course, equal to 3. So beware that 3 doesn't go along for the ride with that exponent operation. Please contrast that with this expression, 3 times x to the 0 power. Well, here the entire expression in that base is going to be raised to the 0 power. And again, anything to the 0 power, no matter how simple or how complicated, is always equal to 1. Let's look at part E. 4 x squared y cubed z to the 0 power. Well, again, there are implied multiplications going on between these exponent operations. So let me go ahead and explicitly write out those multiplication indicators. So 4 times x squared times y cubed times z to the 0 power. Well, the only thing I can really simplify here is z to the 0 power. It equals 1. And of course, I can ignore a redundant multiplier of 1. Anything times 1 is itself, of course. So if z to the 0th power equals 1, the remaining simplified expression is 4x squared y cubed. All right, the author wants to investigate another rule for exponents, and to that end, we will try to motivate this rule with a simple example. Let's say I've got an x cubed inside parentheses raised to the 2nd power. All right, well, if I raise something to the 2nd power, that means I multiply it by itself twice, right? 2 factors of the base being multiplied. X cubed times x cubed, well, of course, from our first rule today, if you multiply the same bases, you keep the same base and add the exponents. Notice I could have gotten from here to here right away just by multiplying those exponents, right? And that is the rule our author wants to list next. He calls it the power rule. for exponents. Some books call this a power of a power rule. If you've got a power of a variable or a numerical expression raised to another power, you keep that same base and multiply the exponents. Power rule for exponents: x to the nth power is x to the m times nth. Right? So this could be our, depending on how you count, our fourth rule for exponents today. All right, let's look at example 10. In the text on page 347, right at the bottom, it says simplify the following expressions. All right, first one, part A, we've got x cubed raised to the 5th power. Well, we know that a power of a power rule says multiply the exponents. So 3 times 5 is, of course, 15 at the exponent level. X cubed to the 5th power is x to the 15th. Let's look at part B. Here we've got a numerical base, 3 to the 4th power, in turn squared. All right, I won't jump to the calculator. I'll just see I've got a power of a power here, as in this rule. All right, so 3 to the 4th squared. Well, 4 times 2 is 8. I get 3 to the 8th power at the exponent level. Okay, our book leaves it just like that. How about part C? Y to the 5th power, in turn raised to the 7th power. Of course, power of a power, we multiply the exponents, and I get y to the 35th power. All right, I'm going to need some more room here. Let me get a fresh screen. All right, the next rule our book wants to talk about is, they call it the expanded power rule for exponents. And to motivate that rule, let's look at an example. Let's say example 11 on page 348. And we've got this expression here, a to the x power times b to the y power, in turn raised to the 4th power. All right, if you raise something to the 4th power, that means you take 4 factors of the base expression. So let me write it out in brute force fashion here. Again, we're going to be looking at a shortcut here in a minute. All right, so I've got all these 4 fractions being multiplied. The associative rule for multiplication and the commutative rule for multiplication says I can arrange all these factors any way I like. I've got 4 factors of a in the numerator, 4 factors of x in the numerator, similarly 4 factors of b in the denominator, times 4 factors of y in the denominator. All right. And of course, these powers of a I can crunch together and express that as a to the 4th power, times 4 factors of x can be simplified as x to the 4th power. Downstairs, 4 factors of b, it's b to the 4th power, and 4 factors of y is y to the 4th power. So what have we done here? Well, we've really taken this exponent and distributed it over all factors in this product and quotient. Right? So to simplify things in the future, we're going to cite a expanded power rule for exponents. Again, this is listed in the middle of page 348. Let me write this out. Expanded power rule for exponents. If I've got a product or quotient involved in a base that's in turn raised to a different power, I can really distribute that exponent over all factors in that product and quotient. So I don't have to write write out that nasty expression that he did in the last example. Right? Expanded power rule for exponents. Again, depending on how you count, maybe our fifth or sixth rule for today. All right, in light of this new rule, I'm going to work through example 12 on page 348. All right, part A says 5x squared. Simplify 5x squared. Well, of course, if I've got a product raised to a power, I can really distribute that exponent over that product. I could call this 5 squared times x squared, invoking my expanded power rule just on a product. 5 squared is 25, and x squared is, of course, x squared. All right, so that would simplify just to 25x squared. How about minus y cubed? Well, don't forget, having a negative sign in front of a variable is really like having an invisible factor of -1. So if I've got a product here, minus 1 times y cubed, I can really distribute that exponent over that product and then simplify. -1 to any odd power is going to be -1 times y cubed is, of course, just y to the third power. And I would just write as a final answer this minus y cubed. Right? So notice the difference here. Negative of y cubed is really the negative outside the exponent operation of y cubed. Part B. Let's look at part C. 4x y to the fourth power. Again, simplify. Here I've got 3 factors in a product, all raised to the fourth power. And of course, I can then just distribute that exponent over all 3 factors of that product. Right? 4 to the fourth power. Well, 4 to the fourth power is 256 times x to the fourth power. That can't be simplified any further. Times y to the fourth power is just, of course, y to the fourth power. Again, example 12, part D. Let's say here we've got minus 2y over 3z. That's the base of this exponent expression. And of course, the expanded power rule for exponents says I can then distribute my exponent over all 4 factors of that product and quotient. So minus 2 squared is positive 4. Y squared is y squared, of course. 3 downstairs, 3 squared is 9 in the denominator. And of course, z in the denominator, z squared, is just z squared. All right, final answer here, 4y squared divided by 9z squared. Let's do another application of the expanded power rule. All right, example 13 on the bottom of page 348 says this. We're asked to simplify this nasty looking expression, 9x cubed y squared divided by 3xy squared, all that in turn raised to the third power. All right, well, the first thing I'd want you to notice here is that, well, 9 can be divided by 3 evenly. X cubed over x can be simplified to a simpler expression. Of course, y squared over y squared, those will cancel each other out. So before I apply this outer exponent, I'll want to simplify first within the base. Simplify first within the base before applying this outer exponent. This is almost always a good thing to do. All right, let me erase these notes here. All right, so I'll work on the coefficients first. Hang on a minute. All right, let's simplify within the base. I will hold off on this outer exponent. 9 divided by 3 is 3, is it not? So 3 can go into 9 3 times, and I'll leave a coefficient of 3 in the denominator, or in the numerators, all right? Similarly, x cubed over x, one factor of x in the denominator will cancel out all but 2 factors of x in the numerator, so I'll have an x squared left in the numerator, and of course y squared over y squared, well, that's just y to the 0th power, or just 1. All right, so I'll have a denominator equivalent of 1. All right, dividing by 1 is redundant, so I can really say this is 3x squared to the 3rd power, and now I will invoke my expanded power rule for products here. 3 cubed is 27, and x squared cubed is x to the 6th power. All right? Was that a little fast? Let me go a little slower on that. 3x squared cubed is equivalent, since this is a implied product here, equivalent to 3 cubed times x squared cubed by our expanded power rule for exponents. 3 cubed is 27 times x squared cubed, power of a power. You multiply the exponents, and we can write this as a final answer, completely simplified, as 27x to the 6th power. All right, let's try another one similar to this. And these take a lot of room, so let me get another sheet here, another screen. Example 14 in our text. This is on page 349. Again, similar to the last one, we are asked to simplify this nasty looking thing, 25x to the 4th power times y to the 3rd power divided by 5x squared y to the 7th, all that raised to the 4th power. All right, if we simplify within the parentheses first, we will be bypassing a lot of redundant work we'll have to do later. All right, so let me go and do this. Let me make a note here. Simplify within the base expression first. Will save you ink and effort and might keep you from making a mistake down the line. 5 goes into 25 5 times, right? So again, I'll leave that outer exponent hanging. All right, this will leave me with a 5 factor in the numerator. X to the 4th over x squared. Well, 2 factors of x in the denominator will cancel out all but 2 factors of x in the numerator. And y cubed over y to the 7th. 3 factors of y will cancel out 3 factors of y in the denominator, leaving 4 factors of y in the denominator. All right, I've simplified as much as I can within the base. So now I have no choice but to really distribute my outer exponent over these 3 factors of the base, product, and quotient. Okay? 5 to the 4th power. Well, let me write that out. 5 to the 4th power times, in the numerator now, x squared to the 4th power. I'll simplify that in a minute. Divided by y to the 4th power to the 4th power, and I'll write it out and simplify it in a minute. Okay? Almost done. 5 to the 4th power, if you go to your calculator, that's 625. That's 5 times 5 times 5 times 5. X squared to the fourth power. Well, again, power of a power, you multiply the exponents. I would call that x to the eighth power. Over downstairs, I'll get y to the fourth power. Power of a power, multiply the exponents. 4 times 4 is 16 at the exponent level. Okay? All right, let's do one more example today. There's one more in the this section of the text on page 350. Let me get a fresh screen. All right, example 15. And this is on page 350. We are asked to simplify the following expression. 2a to the fifth b cubed raised to the fifth power times 3a squared b. All right, now this is an implied multiplication here in the book. I'm going to go ahead and make it explicit with a dot. So I've got a multiplication operation going on, an exponent operation going on. So clearly by order of operations, I'll raise everything in this first set of parentheses to the fifth power first, right? So I'll take everything here, raise it to the fifth power, and then perform this secondary multiplication, okay? All right, expanded power rule says, all right, 2 to the fifth power. 2 to the fifth power is 32. 2 times 2 times 2 times 2 times 2. A to the fifth power to the fifth power. Well, power of a power, you multiply the exponents. I'll get a to the 25th power, right? B cubed to the fifth power. Well, that's going to be b to the 15th power. So that takes care of this outer exponent working on this first set of parentheses. Right? Don't forget we've got to multiply eventually by 3a squared b. And I'll go ahead and apply my commutative and associative law. I'll multiply the coefficients together first. 3 times 32 is 96 times a to the 25th times a squared is a to the 27th, right? You keep the same base and add these exponents. 25 plus 2 is 27 times, in turn, b, well, b to the 15th times b, well, b is just b to the first power. Don't forget about that invisible exponent here. So final answer is 96, a to the 27th, b to the 16th. All right, this concludes section 6.1, Exponents.